All right, everyone, I'm back again with more from Chapter 8. So this is AP Test Prep number 52. And this one is looking at conservation of momentum in two directions. So this is where trig makes an appearance. And this time we are looking at center of mass velocity and how that changes with conservation of momentum. So the question says, a car has a mass of 2,000 kilograms and approaches an intersection with a velocity, this is mass A. VA is 38 meters per second to the east. I'm going to just put VAX there, actually. And then I'm going to put VAY equals 0. Just to get it broken down into those two dimensions right now. So we see that in the X direction, it's going 38 meters per second. In the Y direction, it's going 0 meters per second because it's directly to the east, which is going to be in our X direction. Then we have car B, which has a mass of 3,500 kilograms. And it approaches the intersection with a velocity of 35 meters per second, directed 63 degrees north of east. So if we look closer at that one, this is 63 degrees north of east. So here's our east and here's our north, and we're going north of east at 53 meters per second. So if we look at our VA in the X direction, that's going to be our adjacent component. That's this component here. So it's going to be 53 cosine of 63 degrees. And then our VA in the Y direction is going to be 53 sine of 63 degrees, because that's our opposite component. Okay. Let's see what else it tells us. The two cars collide and stick together. So that tells us that we have an inelastic collision, right? So they are not bouncing off each other. They're not elastic. They are sticking together. And then it says, will the center of mass velocity change as a result of the collision? Explain why or why not. And then calculate the center of mass velocity before and after the collision. Well, we know that the center of mass velocity of the system isn't going to change because momentum is going to be conserved in this collision. So what we can do is calculate the center of mass velocity before and after the collision. It makes it kind of obvious that you're applying conservation momentum because it says, will the center of mass velocity change? And then it says, calculate the center of mass velocity before and after. So we can guess that we're going to see it staying the same. All right, so let's look at our conservation of momentum equation. So we have MAVA. Let's look at the X direction. Instead of adding new variables, I'm just going to write them in their own spots. So MAVA plus MBVB equals M of A plus B times V, I'll call that VX. I'm going to get rid of this parenthesis here because I don't need it. Okay, so in the X direction, so we can solve for Vx just by dividing by M of A plus B. I guess I really want the parentheses to be right there. Yeah. Do that up here too. Okay. So now we've got, it's better, 2,000 times 38 plus 3,500 times 53 times 63 cosine equals that divided by, what is that, 5,500. So we get 29.1. meters per second. Now the y direction. So we have m, I suppose I don't really need to rewrite the whole thing. Oh, m a v a plus m b v b over m a plus b equals the velocity in the y direction. So we've got 2,000 times 0, so that one's just going to go away, plus 3,500 times 53 times 63 sine is that divided by 5,500 again. So that's going to give us 30.1 meters per second. So now to find our actual velocity, does it ask us to do that? Calculate this in? Yeah, perfect. So now we're going to do 29.1 squared plus 30.1 squared equals that. We square root that. So that gives us 41.9 meters per second. Now we need to figure out our direction. So our y is, this is 30.1, this is 29.1. I should actually draw it like this. And we're trying to find, so we know that this is 41.9, but we need to find theta. 30.1. Okay, so theta is going to be, we can do tangent of 30.1 divided by 29.1. That gives us 45 degrees. Actually 46 degrees. So we're at 46 degrees north of east at 41.9 meters per second. Okay, so that is all. So this gives us the direction of our velocity after the collision, but this is also telling us the center of mass velocity before the collision, right? Because these are actually the same equation. We would use the same thing, except this would be the velocity of the center of mass in the x direction. So because momentum is conserved, this is the same thing before and after. All right, enjoy.